Thank you. Hi everybody. Picture this. There's three students in an operating systems lab at UNSW, and we've been asked to come up with a project for a summer student who we haven't met yet. We'd noticed that TI had recently announced the new OMAP4430 processor and a new development kit based around it called the Panda board. And we took a little bit of a deeper look into what this processor actually was about, and we found that it had some interesting features. And one of those features was actually that it was not just a dual-core Cortex A9 ARM SoC, but it also had two Cortex M3 microcontrollers on there as well. So in total, general purpose, we've got 4 cores available to us on this chip. At the moment, prior to this work, Linux only looked at the A9 cores, so they're presented in a typical symmetric multiprocessing fashion. So you end up with a system that looks like that. It's not got 4 cores, it's got 2 cores, but your typical SMP system looks like that. And all the cores are identical, and they all share a single memory. x86 gets a bit more complicated. Can that work? Yes, it can. And you might get a NUMA system where you've got 2 packages, but they all have identical cores. And even though there might be 2 separate memory controllers, the hardware is pretty good at hiding that fact and presents a single address space to the operating system. And that makes it easy for memory to be shared amongst all the different cores, and individual processors can run in parallel and work well together. So I'm going to now introduce this concept of heterogeneous chip multiprocessors, where you've got one package still, but you've got multiple different cores. Now those cores, I'll talk about how they can be different in a moment, but they also still share a single main memory, so you can conceivably run a parallel task on there, and it can work similarly to the way the traditional CMP works. So how can you introduce asymmetry into a chip multiprocessor? So you might have multiple cores, but they run at a different frequency, for example. So you can do this nowadays with some AMD chips. You can run different cores at different frequencies. In the case of the OMAP chip, the 2 cores have different pipelines and different caches and TLBs. And all of this results, furthermore, you can get instruction set asymmetry. So more details on this in a second, but for example, your Atom might not support SSE4 that the Core 2 does. And if you have them on the same die, you can't run the same process that uses SSE4. So why are we starting to see heterogeneous systems these days? Well, first of all, for energy efficiency, if you've got a phone that has a large processor in it, you may not want to keep that processor active the whole time because it uses a lot of energy. A small core, on the other hand, has a small die area and can be much more energy efficient depending on the type of workload that you run on it. And this allows the big cores to stay asleep while you run a less compute-intensive workload on the smaller core. Obviously, if the core is smaller, you can fit more of them in a given area, so you can run parallel tasks on the small cores and still maintain single-threaded performance on the big core if you need to. So prior work has addressed some potential models of which an OS can be designed around to take advantage of heterogeneous processors. I'm going to go into some details about them right now. First of all, there's this idea of a restricted model, where you restrict the kernel and, well, you restrict user space programs to a subset of the features that are available on both the core types. Obviously, if you do this, you may not get advantages from certain features that the big core may provide, and your performance will not be as good as it could potentially be. The second model that's been presented is a hybrid model, and that basically allows the program to interrogate the system to detect its capabilities and then use whatever capabilities it finds. The This is achieved, for example, on x86 systems by use of a CPU ID instruction. You can work out whether or not you've got SSE, and then you can potentially change your processor mask using the shared set affinity system call, and your task will get migrated to the core that has the features that you want. Then there's a unified model. Similar to the hybrid model, we allow programs to use a combined set of features, but we let the kernel deal with the problem of migrating between the cores using what's known as fault and migrate. So if you execute an SSE instruction on an Atom, it's going to fault, and then the processor can say, oh, that's an SSE instruction, I know which core supports that, migrate over to that core, run the program on that core. And following a similar idea, you could, instead of migrating the entire process, you could just proxy the instruction in a lightweight process and then leave the main process on the other core. This requires, I say, a lot of OS trickery, but it also has performance overheads as tasks are migrated between the cores on an instruction by instruction basis. So you need to be careful about how that's implemented. And then, of course, there's the model which Linux is currently implementing, which we've called a distributed shared memory model. So basically the OS doesn't provide any mechanism. It's a third-party tool which you use to get your code running on the different core. So for example, with the cell processor and the SPUFS framework, the cell processor has 8 synergistic processing units which provide a limited set of instructions, and then the main program that runs on the big core can distribute tasks to all those little cores using the Unix file system model. And that's nice. What's currently provided for the OMAP is called syslink, and it basically provides the same mechanism, and it just allows you to stick a binary blob in memory somewhere and then set the small core going on that. And it runs in its own OS framework that's proprietary and provided by TI. There's various advantages and disadvantages to each of those models. Simon's going to go into a bit of detail about what we actually implemented in a few minutes. So I'm just going to go into a little bit of detail about the Panda board now. So that's the Panda board there. It has the OMAP sock in the middle there. It provides a whole array of different features, Ethernet, serial console, USB host, DVI out, etc. And it's the first platform that's based around this chip, so we're pretty excited when this got announced. And as part of the announcement, TI started this Panda board early adopter program where they'd actually give you a free Panda board if you described a project that sounded awesome, and everybody thought it was awesome. So we presented this project, well, we proposed it to them, and they chose it. So we ended up with a free Panda board. The plan was to try and get Linux to be able to schedule tasks on any of the cores available. And in doing that, we would basically treat both of the cores as general purpose cores, and you could execute whatever you like on either core. And the idea was to examine the effects of offloading certain things to the small core versus the big core and look at how that affects energy consumption and efficiency. So this is the chip itself. The things around the outside are the things attached to it. You can see in the middle we've got the things in red, the compute cores. There's more than just the Cortex A9s and the Cortex M3s on there. There's DSPs and video accelerators and decoders and all sorts of stuff, and facial recognition units and everything, but they all have different instruction sets. But the A9s and the M3s, as you can see there, they both support the Thumb2 instruction set. So conceivably we could run tasks on either processor and it would just work. But there's some differences between the subsystems which make it a little bit difficult. We foresaw some of the problems before we started, and we thought we could probably overcome them, whether they be high efficiency implementations or not. We decided to go ahead with the project. As you can see, the clock speed of the two cores varies quite a lot. One's about a quarter, 266 megahertz versus 1 gigahertz. So right there's performance asymmetry. The A9 subsystem it's presented as a traditional SMP, so it's got shared caches with cache coherency implemented in hardware, while the M3 subsystem, there's no common shared cache between the two subsystems, so cache coherency was always going to be an issue, but we'll come to that a bit later. So as I said, they implement a common subset of instructions, thumb2, but there's some differences, which means that neither the M3s nor the A9s actually implement the whole thumb2 ISA. For example, the M3 has special division instructions which are provided to improve its integer arithmetic, and there's some instructions on the A9s which the M3s don't implement, and the A9 also has this optional floating point unit and DSP extensions which the M3s don't have. So if we wanted to use those features, we'd have to migrate to the A9. Additionally, the system ISA, which is the instructions that are used to manage caches and interrupts and all of those sorts of system functions, are completely different. So we need to be able to deal with that when we start talking about implementation. So I think I'll hand over to Simon now, who's going to go into some details about our chosen implementation.
Sorry.
There you go.
Okay.
That button there.
Thanks. Good. Okay, so we started this project by looking at the current support for thumb2 in Linux. Linux already has support for thumb2, and it was an option in the menu config which we enabled, but initially it didn't work. There were some problems with it. First of all, there were some lines of assembly that we found that wouldn't compile for thumb2. Thumb2 has, because it compiles to 16-bit instructions, it has some literals that it can't use, so we had to do some hacking to enable those. Also, there was a problem with the booting. The second A9 core started in ARM mode, even though we had compiled the kernel for thumb2, so that needed to be fixed. Also, I noticed that the kernel didn't compile completely to thumb2. There are these user space helper functions. They're designed to be accessed by user space, so they're compiled as ARM. This is the ABI, and glibc has switches the CPU to ARM mode before it calls them. So naturally, when we compile the kernel as thumb2, we still need this to work. So that's why the kernel still compiles these as ARM. However, when we start putting Linux on the M3, we're going to have to change this. So this requires patching glibc. Yes, so the first, and after those, thumb2 worked on the A9s, so the existing SMP Linux was running. Next, we need to get Linux running on the Cortex M3s. Initially, there was no support for standard Linux running on the Cortex M3s. This is because the Cortex M3s are small embedded microcontrollers which are designed to run in systems without much memory management support. So there was no existing support. However, there was some support for running UC Linux on the M3s. UC Linux is a fork of the standard Linux that is designed to run on small microcontrollers like the M3. So our first step was to take this support from UC Linux and merge it into standard Linux and try and get an M3 running standard Linux. The hardware didn't really support booting directly an M3 core. So to do this, we partitioned the memory to 2, and we were trying to bootstrap an M3 from the current running Linux on the A9s. When we were doing this, we came across a whole bunch of problems. I'm going to go through 3 main problems. There was problems with memory management, obviously, because the M3s are designed without support for memory management. There was also some issues with the exception handling on the M3s. And then we had some issues with tool chains. So first, memory management. I'm going to briefly go through what memory management is, just quickly. Memory management is all about creating virtual address spaces for user space applications and controlling how they map to physical memory. For each address space, we need a page table. This defines these mappings. And in order to do these translations, we need a piece of hardware called a memory management unit. The MMU does the translations and often does permission as well, so can restrict pages to being read-only or execute-only. As well, the MMUs use a translation look-aside buffer to cache these mappings. This is just for performance reasons. And these TLBs can either be software loaded or hardware loaded. Software loading requires the kernel to trap a fault and look up the page table manually and insert the entry, whereas the hardware walkers are implemented in hardware and can do all this much faster. Okay, so on the OMAP, for the M3s, the M3s themselves are designed without memory management, so they don't include an MMU. However, TI was kind enough to put 2 MMUs onto this subsystem. Now, it's kind of weird to have 2 MMUs. These aren't like the A9s, which have had 2 levels of MMUs, but these are 2 separate MMUs. And also they're connected in series, which is kind of odd, because this means that an address is first translated by the level 1 one, and then that translated address is translated again by the level 2 MMU. Yeah, I don't know. Also, these MMUs are both shared between both Cortex M3s, which means that we can't run a separate user space application on each of them, because that would require 2 different address spaces, which we can't do with. So it might be possible to run 2 threads from the same user space application on these cores, but to start with, we're just stuck with using 1 M3 core. So we need to implement enough memory management for Linux using these provided MMUs. Linux expects MMUs to have a few features which these ones don't really support. First of all, supervisor mode permissions. This is where this allows for TLB entries to have a second set of permission bits for when the CPU is in kernel mode. Linux uses this to protect kernel mode memory when you're in user space, and then automatically enable access to kernel mode when you trap into the kernel. Neither of these have that, so we have to maintain a separate address space for when you're inside the kernel as opposed to in user space. This involves creating a shadow page table, which I had to do. Also, neither of these TLBs are tagged. Tagged TLBs is when TLBs are aware of which address space you're currently in and you don't need to flush the TLB every time you do a context switch. Unfortunately, this impacts performance, which is unfortunate. A more advanced memory management technique used in Linux is copy on write. I'm just going to quickly go through how that works. It's used in Linux for sharing pages and mainly for performance reasons. So say we have a parent process that has a bunch of mappings to physical memory, and it can read and write those mappings, and then it wants to fork. So when we fork, we duplicate this process. Instead of copying all the physical memory blocks, we instead create the child with the mappings to the same physical pages, but we mark both the parent and child as read-only. So both the child and parent can read from this memory, but as soon as the child tries to write to this memory, this causes a fault because it's read-only, and then Linux catches that fault, duplicates the blocks that the child was trying to write to, and then repairs the child's page table with a read-write mapping to the new block. Okay, so to do this, we need to support read-only pages. However, we initially wanted to use the L2 MMU here because it has a hardware walker and it's a fair bit bigger than the L1 one. But unfortunately, it doesn't support loading permission bits. So to implement read-only pages, we have to use the L1 MMU. Now the L1 is software loaded, so exclusively using the L1 would be really painful for performance. So we tried to use a combination of these to get the best of both worlds. So to do this, required a bit of hacking. I'll step through it to try and explain it. So first of all, for read-only pages, we wanted to remove them from the page table so that the L2 hardware walker didn't pick them up initially. So when this means that there'll be a fault because neither TLB has an entry for this and the hardware page walker can't fill in the entry. On this fault, we map in an entry to the L1 with the correct permissions, as well as an entry to the L2. We don't want to do any translation at the L1 level, or the L2 will get confused between virtual and physical mappings. So we just map it to itself. And then at the L2 level, we have to add an entry in to stop the L2 faulting and to do the translation. So, yeah, this is a little bit roundabout, but in the end, we can use the hardware walker to load the read-write pages, which is good for performance, and we can still implement read-only pages.
That means, sorry, can I have a question?
Sure.
At the end?
Sure.
Okay. That means if you evict something from your L1, which eventually happens, you have to kick back from the L2 level 2 as well, or you're not going to get a fault again next time.
When we evict something from the L1.
So you get 11th translation coming into.
Yeah, so what we did was we tried to keep the L1 and L2s in sync. So the first 10 entries in the L2 we marked as locked, so the hardware walker wouldn't overwrite them, and we kept them exactly the same as the ones we loaded into the L1. That way the first 10 entries were in sync, and the rest were used for read-write mappings. Okay, another problem we came across was with the exception model on the M3. So the exception model is kind of weird when we consider it in the context of memory management. But so the M3s, when they fold on an exception, they save the state of their CPU to the current stack pointer. This means when you're in user space, it saves it to the user space, the user stack. And when you're in kernel mode, it saves it to the kernel mode stack. And that's fine when you're in a microcontroller and there's no memory management. But as soon as you try and do dynamic stack allocation, yeah, you run into problems. So quickly, Linux, initially when you start a process, it allocates a really small stack and puts an invalid page off at the end of the stack. And then when the user program faults on that invalid page, Linux knows that the user program's gone past the end of the stack and it assigns more space, and the user program continues. However, on the M3, obviously when it faults on this page at the end of the stack, it tries to save its exception to CPU state to the stack pointer, which is invalid because you're past the end of the stack. So that raises another exception, and you lose the state of the CPU, so you can't resume the user process. So that means stack faults are unrecoverable in the M3. So to get around this, we had to pre-allocate and pin the entire stack, which is kind of painful, but it works. Another problem we had was with the tool chains. So yeah, we just, at this point we had Linux running on the M3. This is the first version of standard Linux running on the Cortex M3, so we had problems with getting existing tool chains to build user space applications. First of all, glibc wouldn't compile to pure Thumb2. You can compile it for Thumb2, but it has a whole bunch of optimizations done in ARM assembly, which we had to get around, and so that involved patching that. Also, the calls to these user space helpers from the kernel, in the kernel, they still assume that these user space helpers are implemented in ARM, so we had to change that as well to keep the CPU in thumb mode when calling those. Also binutils. Binutils uses a procedure linkage table. It builds this into a binary when it's trying to use shared libraries. This allows dynamic linking. This is all done in ARM assembly and is fairly complicated. We didn't have time to redo this, and it's easy enough to compile things as static, so for now we're just stuck with static binaries. Yeah, so now we had standard Linux running on the M3s. It was fairly painful, but it worked, and we had user space applications that ran on it fine. So this is still running alongside an A9. Yeah, but that wasn't our main goal anyway. So now we could move on to our main goal, which was trying to get Linux to run on both the A9 and M3 cores. Etienne went through a few models of ways to implement OS support for this type of system, and we chose a restrictive model. This restricts all user space programs to the subset of common features available on both types of cores and the common ISA, the common parts of Thumb2. We did this mainly because we wanted to provide an S&P-like system that allowed you to schedule tasks on either core without worrying about features, and also we wanted to investigate energy efficiency, which would involve offloading tasks, so we wanted to be able to run as much as Linux and the user programs on the M3 as possible. To do this, there was a whole bunch more problems. I'm going to go through a few. to implement the restrictive model, we had to be able to compile into this subset of thumb2, which had some challenges. We also wanted to produce a single image of Linux that could run on both A9s and M3s. Linux obviously doesn't do this at the moment, so there's a bunch of changes that need to be made there. We also need to support synchronization between the two subsystems. And we wanted to support live migration for offloading tasks. And we had some problems with interrupts, which I'll go through. So first, compiling for this subset of thumb2. binutils, by default, only compiles for a single architecture. So we needed to create a new architecture which represented this subset that we wanted to use. And we needed to compile all user programs using this. Also, when we were compiling the kernel, we wanted to compile the majority of the kernel using this. However, we also needed to support two sets of architecture-dependent functions, which both used the different system ICEs and special registers, such as the CP15 for the A9 and some the mask registers for the M3. So we needed to be able to compile both of these. Next, we needed to modify Linux to be able to boot both the A9 and M3. So the ARM port of Linux is sort of a mess, and it has these concepts of boards and platforms and processors and stuff. Jonathan Corbett talked about this earlier in the kernel report. One of their main goals, though, is to provide a unified ARM kernel that can run on all the different types of ARMs processors. There is sort of support for that at the moment. There is this idea of processor abstraction, which you fill out when you create a new platform. It provides function pointers, or it's a struct that provides function pointers for all the platform-specific operations like caching and TLB and some CPU-specific things. So this was a really good start for what we were trying to do, because it let us compile two sets of functions for different processors into the same Linux binary. However, this didn't quite cover all the differences between the Cortex A9 and M3s. There were some architectural differences which weren't covered by that, so like interrupt enabling and disabling. We also had to provide two sets of exception handling. The M3's exception handling is very different from the A9's, so we needed to include both of them. And then we needed to be able to get the A9 to run and look at the A9's version of this struct, and the M3 to run looking at the M3's version of these functions. So to do that, we did some MMU hacks and made permanent mapping into the M3 that would map the M3's processor information over top of where the Linux expects to see this. This would allow the M3 to see the M3s and the A9 to see the A9s, and that worked pretty nicely. The next problem was synchronization. We need a way of synchronizing between the cores like you do on any SMP system. This is made a little bit more difficult because the Cortex M3s and A9s are in separate subsystems. ARM generally uses exclusive monitors to implement atomic operations. These work on between the two A9 cores. They use the Snoop control unit to monitor the bus to make sure things haven't changed while between your load and store. This won't work when you try and go between the M3s and A9s. So we need a way of doing this. TI has provided a hardware spin lock module, which is kind of perfect. It implements hardware supported spin locks that we can use. So we had to change all the synchronization primitives in Linux to use these instead of the traditional exclusive monitors. Also, cores need a way of signaling each other. This is generally done using inter-processor interrupts. Linux expects a situation like this in SMP where every core can interrupt every other core, and that's not what we have. We have this, where the A9s can interrupt each other and the M3s can interrupt each other. There is no direct interrupt between the A9 subsystem and M3 subsystem, let alone the individual cores within the subsystems. So TI provided a mailbox thing, which is meant for communication between subsystems. It provides an interrupt line, a single interrupt line to each subsystem, which is not ideal. We'd prefer to have more than one to each subsystem, but this will do, we can then forward interrupts around within the subsystem if we need to. The next, we need to support migration. We had to have some special consideration when migrating between the two different architectures. We had to make sure, first of all, the page table formats are the same. This is luckily generally the case, as the L2 MMU on the M3s reads the same format as the A9's MMUs. However, because we were doing this hack to get read-only pages working, we had to invalidate a whole bunch of entries in the M3. So when we migrate between the two, we have to go back and walk the entire page table to fix this. It's not great for performance, but it worked.
So you can't have a multi-thread application with one thread on the A9 and one thread on the M3?
Not at the moment. Also, exception handling. When a user program takes an exception and enters the kernel, it can then potentially be migrated. And when it returns back out of the kernel, it returns via the path that is left on the stack. If you migrate between these two different architectures, the path, say from the M3 to the A9, the process will then try to return via the M3's exception handling routines, which won't work on the A9. So we had to check the CPU ID on the way out to make sure that we return to the correct exception handling things. Also, the M3 status registers are different, and it stores registers to the stack differently than the A9 does. So we need to keep these consistent if we don't want to have to duplicate half of the Linux code that uses this. Also, when we migrate, we need them to be in a state that the other exception handling code can read. This involved manipulating stuff on the stack and in the exception handling things, which was fun. But after this, we had live migration working, where we could task set or shed set affinity, and this would migrate tasks between the A9s and M3s, and it worked, which is good. Interrupts. This was a problem because in S&P systems, Linux expects that the CPUs can all access the available hardware. However, in this system, the A9 and M3s can't access each other's interrupt controllers. This means when we're trying to mask an interrupt, the M3 can't mask interrupts that are mapped to the A9. It has to do a request to the A9 to unmask that interrupt. And also, not all the interrupts are mapped to the M3 subsystem. There are a whole bunch of interrupts, like the serial port, which aren't mapped to the M3 subsystem. This means that we can't run Linux completely on the M3 like we would have liked to. Which is unfortunate, but yeah, so at this stage, we had Linux that runs on both M3 and A9 and can migrate between them. So we thought that it'd be good to do some benchmarking to investigate the overheads of these changes that we made. And we used the Embassy benchmark suite, which is designed for embedded systems. It has a wide range of workloads that are separated into 4 separate suites: automotive, telecommunication, networking, consumer. They're all different. And this is the performance we got when we, this is a comparison of the runtime for all these Embassy benchmarks running on a single A9 core, first in our unmodified system, and then in our modified system. As you can see, performance is really, really bad, like 50 times slower. And this is because we had caches disabled. Yeah, so caching. Caches are part of the memory hierarchy. They sit between main memory and CPU. They're designed to improve memory latency and just the general performance of systems. In multi-core systems, we have 2 options. We can have shared caches or local caches. Shared caches tend to be more complicated and slower because they have to be able to support multiple requests from different cores at the same time. Local caches tend to be heaps faster because they can be closer to the core and a lot simpler. So most people use a combination of both of these to get the best of both worlds. However, when you do that, you run into cache coherency problems. This comes about with local caches. So for example, if the first A9 writes to a piece of memory, that memory is stored in its local cache, the changes it made. And then if the second A9 tries to read, it will read from its local cache and read the old value of the memory. This is cache coherency problem. So to fix this, we need some sort of protocol that will notify other cores of changes to memory when you make them. This is traditionally done using Snoop control. It's an efficient way of doing it, where a piece of hardware that sits on the bus and monitors memory accesses and ensures that the caches are kept coherent. So in our system, the A9 subsystem is all nice and cache coherent. It has a Snoop control unit to keep its local caches coherent. The M3 has a shared cache, so it's all good. However, as soon as we try and do anything between the two, we run into cache coherency problems. First of all, there's no shared cache, so we have to do all our sharing at main memory, and there's no hardware support for any cache coherency. So this must all be done in software. So we implemented a big kernel lock. I know we just got rid of the one in Linux finally, but it's an easy way to implement this cache coherency. So the way it works is, first of all, it restricts one CPU from being in the kernel at a time. And when that CPU enters the kernel, it flushes all its caches to make sure that it reads the latest version of the kernel memory from main memory. And when it leaves, it flushes all its caches to make sure all its changes to kernel memory are written to main memory. However, this is really slow, and I tried to speed it up a bit by adding an interrupt that will signal contention so that the CPUs didn't have to do this every time they entered or exited. But
you can keep the two A9s still together.
yes, this is only between the A9s and M3s. Yes, so using this lock, we had cache coherency, but yeah, it's not great. So let's have another look at performance. Again, we're just comparing the performance of a single A9 running the entire Embassy suite. We'll compare it to a whole bunch of different stages, though, to look at where the overheads came from. So we start off with our unmodified Linux. This is before we touched it for hacking, so this is just running on one A9. And then we changed it to Thumb2. This is the pure Thumb2, the common set between the M3s that had all my changes to Ghibli, all my changes to the tool chain. This introduced a 14% overhead, which is a fair amount higher than we expected. Assumes that, says that Thumb2 should be 95% as fast as ARM. Well, it wasn't. Next, this is Linux with all our changes, but with the M3 offline. There's only 3% overhead with the extra levels of abstraction we put in. And then when we put the M3 online, we get another 20%. This is because the M3, even when it's idling, is still servicing timer interrupts and causing the contention on the kernel lock and flushing of caches, which is really expensive. And then when the M3 is busy, there's a little bit more contention and more overhead. However, at the cost of all this overhead, we have another M3 which we can schedule stuff on. So we decided to look at the performance of the system as a whole compared to the performance without the M3s. So this is a graph showing the performance of an A9 and the unmodified system compared to the performance of the combined performance of the A9 and M3 on our system. Yeah, so as you can see, performance is not great. Yeah, the M3 doesn't make up for all its overheads. It's about 80, a bit less on average. And the worst case is really bad. This is because we're using a software-loaded TLB on the M3 for the read-only things. So benchmarks with a really high miss rate on that. The M3 spends all its time in the kernel trying to refill these pages.
Can't you do that without the big kernel lock?
Refill pages? Potentially.
If you flush and set PT, on PT modification, if you just cache line flushes on the A9 when you modify a PT, you guarantee that you have the value written to main memory. You might be able to have a fast path for you.
We potentially could have written a fast pass for this that might not have forced the A9 to stay out of the kernel while we did this, but we didn't. So that causes really bad performance though. Yeah. Though interesting, the best cases are almost equal, and in one case even higher, which shows promise considering the overheads we had to incur to get this working. Yeah, so I'm now going to hand back to Etienne, who will go over what we did once we got this system working.
There we go. Now that we've got these two types of cores, we know that they're asymmetric, they have different performance. Let's just have a quick look at what it looks like when we run the same task on all the different cores. So here I'm showing just the relative runtime of an A9 versus an M3. As you might expect, it sucks. The M3 is running at a quarter of the frequency. It has a single issue pipeline. It has different branch prediction. And of course, there's the software loaded TLB, which is, on the average case, it's probably adding quite a lot of overhead. But we still have these two different cores. So if we try and use the system in its current state, it's going to suck, because using the round-robin scheduling or the scheduling algorithm that Linux implements these days, stuff will get executed on the M3 during boot, and just basically depending on the load of the system. And even if the A9's available and not overloaded, you're still going to get stuff run on the M3 probably, and that's going to affect the responsiveness of the system, and it's probably going to negate any benefit we get from the system. So what can we do? How do we know, how can the system know what it's going to perform like if it's going to make smart scheduling decisions? Just quickly, we delved into this idea of modeling the performance using a linear model based on some parameters collected on the A9s, such as cache misses, number of instructions executed, for example, to predict what's going to happen if we migrated to the M3. And this is a typical approach that's done in academia, typically not done in the real world because it's so hard to generate a model in the first place. But anyway, we were able to characterize a model based on those performance predictors. Turns out that the TLB miss rate on the M3 is going to be pretty significant, but as we can't measure that directly from the A9, we had to do some crazy statistics to try and predict what the miss rate would be given a different size TLB. So once we include all those parameters in our model, we're able to get a performance prediction, which is within roughly 90% of where it actually is. So 10% error for on the average case for the entire Embassy suite. And that would probably allow the scheduler to make a smart decision on whether or not to migrate a certain task to the M3, which would avoid this problem of everything having the potential to be run on the M3 if we just enable both processes. We haven't actually modified the scheduler to take this prediction into account yet, but it doesn't seem like a difficult step. We have the system working online, so we can basically just say, given this task running on the A9, this is how long it'll take to run on the M3. And that's not an easy feat to solve in this modeling problem. So, as a conclusion, we achieved our goal, which was to get the system presented as a traditional SMP with asymmetric cores. As we've presented, the overheads are caused primarily due to lack of hardware support in terms of cache coherency and TLB support, for example. So with a bit of support from the hardware, we should be able to get the system working quite well. With the right performance counters, the overhead of doing the TLB miss rate prediction is quite high, so it'd be better if we had an actual hardware performance counter that could help us predict the performance of a different size TLB. With the right performance counters, we can predict the performance on a different core quite accurately, and it only took 8,500 lines of code to actually do all this work, and that includes the modeling. So it's a pretty big lot of work inside the kernel, but it's not insurmountable. Pretty much one student working on it part-time for a year managed to complete it. And we haven't pushed it upstream yet. Don't know whether that's feasible, but if you're interested in the nitty-gritty details, even more nitty-gritty than the talk, we've actually got a Usenix paper that's hopefully going to be accepted. If it's not, we'll send it around a mailing list or something for the interested parties. But fingers crossed, the deadline's on Wednesday. Yeah, so we're happy to answer any questions now. Here's the microphone.
How big are the pages on, the 10 pages you have in the L1 TLB on the M3s?
How big are
Yeah, are they 4K pages or variable size?
4K pages.
Right.
It does also have a few larger page sizes, which we had to use to define caching attributes.
And we can put the numbers in.
The one right up the back there.
Have you had TI? Are they interested in what you're doing?
Has TI contacted us? Are they interested? Well, they gave us the Panda board based on this project, so they sort of know what we're doing. We have had some communication with them a little while ago about some of the crazy problems that we encountered. We haven't expressly spoken to them recently, but I expect that they'll want a copy of the Usenix paper as a sort of final part of the project for them.
If there is no further questions, on behalf of Linux Conference Australia 2012, can we show appreciation for Simon Etienne's fascinating adventure? We do have a little token of our appreciation, a gold-plated glass pendant, and I believe in your spare time you juggle cats. Okay, thank you very much.